The usable voice frequency for telephone system ranges from approximately 300 Hz to 3.4 kHz. Here we want to design a filter for telephone speaker to remove high frequency noise. The gain for the low frequency range should be above 2 and the gain for the high frequency range should be less than 0.1. Let's look at the subsystem design procedure we suggested in our tutorials. The first step, we need to translate problem statement to design specification. The second step, we need to choose prototype circuit. Then we need to specify the values for the values of the components in the prototype circuit. Then analyze the circuit. The last step, we need to build the circuit and test it, and check with the design specification. Let's work on the problem statement and translate it into design specification. Here the useful signal is from 300 Hz to 3400 Hz. And we want to remove high frequency noise. So this should be a low pass filter. So from 300 to 3400 Hz, the gain of the circuit should be at least 2. So here we can plot it as decibel, the gain of the circuit as decibel. So we can set the passband gain as 10 decibel. So 10 decibel is equal to 3.16. That's above 2. And if it's 7 decibel, is equal to 2.24. At 20 kilohertz, the gain of the circuit should be less than 0.1. 0.1, if we convert it to decibel, that is negative 20 decibel. So when the frequency is 20 kilohertz, the gain should be less than negative 20 decibel. We know at the cutoff frequency, the passband gain is 3 decibel below the passband gain. So that is 10 minus 3 is 7 decibel. Based on our design specification, if we make the cutoff frequency greater than 3.4 kilohertz, in that case, it's going to satisfy this design specification. So anything below the cutoff frequency, the gain of the circuit should be greater than 7 decibel. So there are many low-pass filter prototype circuits available. In this tutorial, we will use a cascaded identical low-pass filters. For the first order low-pass filter, we have shown the circuit here. So we want to cascade it nth order identical filters. The passband gain should be 10 decibel, and we can set the cutoff frequency at 4 kilohertz. As we mentioned, we want to make it greater than 3.4 kilohertz. So here we can use 4 kilohertz as the cutoff frequency. So when the filter is to suppress the frequency at 20 kilohertz at least 30 decibel, that means at 20 kilohertz, the gain of the circuit should be at least 30 decibel below the passband gain. So that is 10 minus 30, should be at least, at most, negative 20 decibel. In our design, we have just picked up the prototype circuit. So when we try to design a cascaded nth order filter, we need to determine the order of the circuit. So the cutoff frequency is at 4 kilohertz. At 20 kilohertz, the gain of the circuit should be 30 decibel below the passband gain. So let's look at the normalized identical cascaded low-pass filters. So here, all the cutoff frequencies have been normalized to 1 radian per second. So we can scale the frequency axis by multiply the frequency by 4 kilohertz. So 1 times 4K is 4K. So here's 1, 2, 3, 4, 5. At this point, it's 5 reading per second. After we scale that by multiplying with 4 kilohertz, so it's 20 kilohertz. So at 20 kilohertz, we want the gain of the circuit to be at least 30 decibel below the passband gain. So let's look at so here's at 20 kilohertz. The first order circuit, second order, third order, fourth order, and let's look at the fourth order. Is the gain of the circuit is at negative 30 decibel. So let's use fifth order to make sure the gain of the circuit will be below 30 decibel below the passband gain. So here the order of the circuit should be 5. So we need to cascade 5 circuits. So we just connect 5 first order low pass filters to make a cascaded identical filters. Here's the output voltage. Here's the input voltage. For the fifth order cascaded low pass filter, the cutoff frequency ohmic C5 should be square root of fifth root of 2 minus 1 multiplied by ohmic C1. Here, ohmic C1 is the cutoff frequency of the first order circuit. For the first order low pass filter here, the cutoff frequency should be 1 over RFC. RF is the feedback resistance. Capacitor is just the capacitance. So in our design specification, we just said the cutoff frequency should be 4 kilohertz. Converted to reading per second, that should be 4K times 2 pi. So that's equation 1, 2, 3. Here we can substitute equation 2 and 3 into equation 1. So ohmic C1 should be 2 pi times 4 kilohertz reading per second. Ohmic C1 is 1 over RFC. In this problem, let's assume that we want to use 0.01 microfarad capacitor. So let's use 0.01 microfarad. We can substitute the capacitance here. So that's 0.01 times 10 to the power of negative 6 converted to standard unit. The only unknown variable is RF. We can calculate that from the equation above. So we got 1.53 kilo ohm. We can use a 1.5 kilo ohm resistor for the feedback resistor. So all the capacitance should be 0.01 microfarad. We have 5 resistors in this circuit, 5 capacitors in the circuit. For RF, we can use 1.5 kilo ohm resistor. So all the RF in the circuit, we can use 1.5 kilo ohm resistors. Notice that we want to make the passband gain equal to 10 decibel. For 10 decibel, if we convert it to the circuit gain, that should be 3.16. So 20 log base 10, 3.16 is equal to 10 decibel. So the gain of the circuit should be 3.16. Actually, we can just change one of the input resistor to make the gain of the circuit equal to 3.16. So Ri should be Rf over 3.16. Rf is 1.5 kilo ohm resistor. So Ri is 470 ohm resistor. So we just need to change one of the input resistors here to 470 ohm resistor. All the rest of input resistors we use 1.5 kilo ohm. So here we just designed the circuit. I'm going to skip this step to analyze the design circuit theoretically. So the next part, we need to build the circuit and check with design specification. Here's our circuit. We have 5 op-amps and 5 capacitors in the circuit. All the feedback resistance is 1.5 kilo ohm. For the input resistors, only the last stage we have a 470 ohm resistor. So this resistor is a 470 ohm resistor. So let's test the circuit and check with the design specification. Firstly, let's check the low frequency range from 300 to 3.4 kilohertz to make sure the gain for the low frequency range is at least 7 decibel. So for the low frequency, let's see, at 10 hertz, the gain of the circuit is 10 decibel. So here, the passband gain is close to 10 decibel. So let's check with 4 kilohertz. At 4 kilohertz, the gain of the circuit is 7.07 decibel. So that means starting from 0 to 4 kilohertz, the gain of the circuit is above 7. So the first design specification is met. Let's check with 20 kilohertz. Here I increased the frequency to 20 kilohertz. The gain of the circuit is negative 21.7 decibel. So at 20 kilohertz, the gain is less than 20 decibel. So the second design specification is met. So we have just checked with the design specification. Our designed circuit does meet the design specification.